At first, good afternoon, everyone. Maybe at first would like to ask to mute yourselves if you are not speaking. And also, I would like to remind you that we will record this session. So in case you have any objections here, please speak up. And now I would say it's a great pleasure to introduce today's speaker, Anders Jerkstrand from Stockholm University in Sweden. So Anders did his PhD in 2011, also at Stockholm University, and then he moved to Queen's University in Belfast for a first postdoc position and to the Max Planck Institute for astrophysics in Garching nearby Munich for a Marie Curie Fellowship. In 2019, then he got an EST grant and returned to Sweden, where he now is a tenured researcher back at Stockholm University again. And during his career, he was and still is working on various topics related to the spectral modeling of supernovae and kilonovae from both a code development perspective. For instance, he developed the ZUMO radiative transfer code, but also application-wise. So I guess we will hear much more about this during the next hour. And yeah, Anders, thanks for giving the seminar today, and I guess you can just start.
Thanks a lot, Levin, for this introduction, and thanks to you and to the organizers for asking me to share with you today my research, which I will be very happy to do. So as Levin said, my research is about modeling supernova spectra and how to use these kind of models to infer properties of supernova explosions from their observed spectrum. What you see here in this picture is the Cas A supernova remnant. But most of the supernovae we look at, they are very far away, so we don't have any spatially resolved images like this. So they are just point sources, and everything we know about them comes from interpreting the light curves and spectra. So these are the sections of my presentation today. I will give you an introduction to supernovae, and in particular the nucleosynthesis that massive stars and the explosion of massive stars produce. Then we will look at the methods of spectral synthesis modeling and this code that Levin mentioned, the ZUMO code, which is the main tool that I use to simulate supernova spectra. Then we will look at three different applications. The first application centers on diagnosing the amount of oxygen that the star has produced and what we can learn from determining the oxygen mass in a supernova. The second application looks at the bit heavier elements, so nickel and iron. So these are explosively made elements, and what can the relative amounts of nickel and iron tell us about how supernovae explode? And the third application is a very recent result where we have detected by spectral synthesis modeling a really massive reservoir of iron in one of the brightest supernovae that we know about. So the supernova landscape looks like this. You all know that there are sort of two types of stars that explode as supernovae. The first type is a massive star. Normally we say that the star is more massive than about 8 solar masses. It could be 7, could be 9, could be 10. This depends a little bit on certain stellar evolution physics. But above some mass limit there, the star will ignite all the nuclear burning processes and form an iron core. That iron core can eventually not support itself anymore, and it will collapse into a neutron star or a black hole. And in this process, you have so much neutrino emission that the mantle and the outer layers of the star, they are blown out into space, and this is the supernova. Then we have all these sort of types of supernova or supernova classes that you see here. So they're called type 2P, type 2L, type 2B, 1B, 1C, and so on. So what are these things? These basically tell you how much of the outer layers of the star have been removed at the time that it exploded. So if you have a type 2 in the supernova name, it means that there are hydrogen lines present. So it means that the star has retained at least part of its hydrogen envelope. Whereas if it's a type 1b or a 1c, there is no hydrogen, so the star has lost the entire hydrogen envelope. In the 1b case, there is helium still in the star, and in the 1c case, there is also no helium. So those kind of stars seems to have lost both the hydrogen and helium layers. And the basic idea here is that if you did not have a lot of mass loss from the progenitor, well, then you go into this category. You become a type 2P or a type 2L supernova. Normally, you have a red supergiant progenitor. And then you may have cases where you have more mass loss, and then you end up in one of these categories instead. This is with weak hydrogen lines, and this is with no hydrogen. This is with no helium. The other supernova type is the explosion of a white dwarf. So white dwarfs are degenerate objects. They are sitting there with carbon and oxygen under degenerate conditions. And if you manage to raise the temperature enough by some kind of accretion process in a white dwarf, you start a runaway thermonuclear burning of this carbon and oxygen, and the white dwarf explodes. And by a sort of strange coincidence of nature, the amount of energy that's released in these two completely different processes is almost the same at about 10 to the 51 ergs. So this, of course, led to initially quite a long period of confusion before people understood that these two completely different objects that produce supernovae. The big differences then is in the ejecta masses. So we have a massive star, depending on the degree of stripping of the envelope, depending on the progenitor mass, you're typically between 2 and 20 solar masses ejecta. A white dwarf is somewhere around the Chandrasekhar mass or a bit lower, so around 1 solar mass. And another big difference is how much 56 nickel, which as we shall see is the actual power source of the supernova, is produced, where we have much more production in the type 1a explosions. Sometimes the supernova explodes into circumstellar, well, there is always circumstellar material present to some degree. If there is a lot of it, then this interaction, basically the collision of the supernova with the circumstellar material, it produces some very distinct features, and then we call the supernovae type 2n or type 1bn if it's a core collapse supernova. If it's a 1a supernova, we call them type 2a. So this is sort of a slightly simplified overview of what we are dealing with when we are looking at different supernova types. Now, mass loss and so on is something that I know is an active research field at Leuven, and one of the sort of main questions we are chasing when we are trying to decode supernova light curves and spectra is to understand how did this outer layers, how was it lost from the star in the case that you have a stripped envelope supernova, or in the case that you have one of these interacting supernovae. Where did the CSM come from, and how did the stellar progenitor lose that mass? And you have two sort of main channels that could be operating. You could have a stellar wind from a single star. Here you have an image of Betelgeuse, and you see this strong mass loss coming out from the star in the red supergiant phase. And we do expect that when you go to main sequence masses of about over 30 solar masses or so, these stellar winds are going to drive the hydrogen off the star. But we also know that a lot of stars, especially massive stars, they are in binary systems. And when the star expands, so typically it starts to become a red supergiant, if there is a companion not too far away, you can start to have mass transfer by Roche lobe overflow. And you may even have a common envelope evolution of these kind of objects. So, and the difference here, or one of the differences, is that here you can also you can remove layers from the supernova also at lower masses. You don't need to go to these 30 solar masses to have strong enough winds here. For both of these channels, we expect that most of the mass loss occurs in the post-main sequence phase. And in general, it's sort of quite uncertain how the mass loss is operating. One of the main things we are trying to answer when we look at supernova spectra and compare observed spectra to model spectra is what is the element production in the star. So one can divide this into two regimes, basically elements that are made sort of during the lifetime of the star in the hydrostatic burning processes. So during the main sequence, you produce helium by hydrogen burning, and then in the post-main sequence, by helium and carbon and neon burning, you produce the heavy elements here, carbon, oxygen, up to approximately magnesium. So we believe that elements up to approximately magnesium in the periodic table, they are made in this process of hydrostatic burning. If you could look at heavier elements, it turns out that they are predominantly made in the supernova explosion themselves. So in this innermost region here, the supernova releases a lot of energy. A shock wave is traveling out here. This is the shock wave that is going to disrupt the star and send it out with these 10^51 ergs. And in this innermost region, the temperature behind the shock is high enough that you will have explosive nucleosynthesis. So here you produce elements on a time scale of approximately 1 second, whereas here you are on 10 to the 7 years. So it's a very different process. And by studying the production of these elements, approximately from silicon and up to the iron group, we can try to say something about how supernovae explode and possibly what was the structure of the very innermost region of the star that collapsed. So I will show you some applications today, in particular from 2 layers of massive stars. So we look at oxygen and magnesium. These elements are produced mainly by carbon burning. And this is something that happens in the last maybe 1,000 years of the star's life. And we will look also at iron and nickel production, which then occurs in the first second when the supernova explodes. Do we understand the origin of the elements well? Here is a table of the 15 most common elements in the universe. And the third column here says sort of the, well, assumed origin or the prevailing ideas of where the elements come from. So you have core collapse supernovae in red and the thermonuclear supernovae in blue here, the white dwarfs. And apart from the Big Bang nucleosynthesis of hydrogen and helium, you see here how dominant supernovae are in element production. We believe AGB stars are probably the main producers of carbon and nitrogen. But for example, one question that's not entirely settled is what role do core collapse supernovae play in the production of carbon? Like what fraction of the carbon in the universe come from AGB stars relative to core collapse supernovae? And in general, maybe the most important takeaway point here is the thing I put in the box down here, that there is really very few analysis of supernovae where we say, okay, this supernova produced so much argon and so much silicon, and by combining this, we can show that this element comes from this kind of explosion. We are sort of only starting to do that. And a lot of these things are sort of predictions from stellar evolution models rather than sort of observationally confirmed results. In the last column here, I write the nebular emission lines that we can use to directly determine the nucleosynthesis of an element. So we look at the spectrum of the supernova, and in order to say, determine how much carbon was made, well, we need to look at these emission lines here and model that emission and infer an element mass. And for a lot of elements, there's not so many lines to work with. For example, you can take neon, which is the 6th most common element in the universe. We have no idea how much neon was produced by any star or supernova. And there is only one diagnostic line, and it lies far into the infrared, so we're not even accessible there with observations usually. For some other elements, the situation is a little bit better. And of course, we are sort of initially focusing on these elements that have at least two good diagnostic lines in the optical regime. So when the supernova explodes, it's initially it's sort of like a hot fireball. It's optically thick, and for the first few months you don't see much. You just see a black body spectrum modulated by some absorption lines, and these are sort of created in the outermost maybe 1% of the stars, just like in the atmosphere of the star. It doesn't really, if you want to determine the nucleosynthesis or if you want to determine the inner structure of the supernova, observations in this phase don't really help you. So what we have to do is we have to wait a few months. And as you see in this graph here, this is a very old figure, but it's a nice illustration of how the history of these things went. So these are supernova light curves reported in the 1940s. And Walter Bade, he realized in 1945 that after this sort of optically thick diffusion phase here, they settle on some kind of exponential tails. And this was a little bit mysterious, because if you explode something, you don't expect it to go settle on an exponential decline. And then Borst, a couple of years later, he said, well, we only know of one good exponential physical process that could do this, and that's radioactivity. And he was absolutely correct. The reason we see supernovae in these phases is because they produce radioactive isotopes. And these radioactive isotopes, they decay then on timescales of months or years, and they provide the power source of the supernova. Keeps it bright, keeps it emitting for several years after explosion. So in 1969, the correct isotope was identified. This is 56 cobalt that has a decay time of 111 days. And these light curves, they follow that exponential decline quite closely. So we have a phase of the supernova which we call the nebular phase. It's approximately between 100 days and up to maybe 1,000 days or so. After that time, most supernovae are too faint to observe. So this is our window. And in this window, we start to see emission from the inner regions of the stars. We are approaching optically thin conditions, and emission lines with their distinct spectral fingerprints, they come out. We see things, for example, here we see hydrogen, oxygen, sodium, and so on. If we can decode these fingerprints, we can determine the nucleosynthesis and maybe even the structure of the supernova. So one tool we are using to interpret these kind of observed spectra is spectral synthesis models. So we take some prediction for the supernova structure. So typically someone runs a stellar evolution code and then explodes the star, and you have then a prediction for what the supernova structure will look like, the composition, the density profile, the amount of radioactive isotopes, and so on. And then we ask ourselves, what should such a nebula be emitting? What should it look like? So we have to simulate the physical processes occurring in the supernova to make prediction for the spectra that they produce. And the code that I use is then the SUMO code, which I developed during my thesis and have continued to develop over my postdoc years. There's basically 5 sort of blocks of physics that you need to address in order to make a realistic prediction of the spectrum. So the first one is to treat this radioactive decays that, as we said, they are the power source of the supernova. So we need to include that. We need to include the transport of decay particles and how they deposit their energy in the supernova ejecta. These radioactivities, they produce a population of Compton electrons. And these Compton electrons, they continue to bounce around in the ejecta, and they heat the gas, they ionize the gas, they excite the gas. This is what makes the supernova glow. And in order to calculate these channels, we solve something called the Spencer-Fano equation, which is basically the Boltzmann equation for these Compton electrons. So this is one of the core modules in a spectral synthesis code. This is also what makes supernova spectral modeling quite different from all other types of spectral modeling. Like, you don't have this thing, for example, if you do stellar spectral synthesis, you don't have these Compton electrons. The other blocks are to solve the energy equation, which we can do assuming steady state in supernovae. So we can balance heating with cooling because the timescales are short. That gives us a temperature. The densities are too low for LTE assumption, so we do have to solve the NLTE rate equations. Currently, what SUMO does here is it treats 22 elements from hydrogen up to nickel with 3 ionization stages, or neutral, singly ionized, doubly ionized, and a couple of hundred excited states each. And finally, we do a radiated transfer, where currently we have a few 100,000 atomic lines, as well as continuum processes. So all these things are coupled to each other. So you basically go around an iteration loop here, and hopefully things will converge into a solution for the physical conditions of the supernova. It is a one-dimensional code, but we have a way to treat mixing and clumping processes in an approximate way. I will not go into the details here, so if you're interested in this, we could address that maybe at question time in case. So the radiated transfer turns out to be something that you need to consider for quite a long time in supernovae. The continuum transfer is not so important after a few months, but the line transfer continues to be an important physical process for many years. What is happening here is basically a supernova is in a homologous flow. So this means that at some point you don't have acceleration forces anymore, and things are just moving radially away from the starting position with the velocity proportional to the radius from the center. So this is just like the galaxies in the Hubble flow. Everything is moving away from everything else. And what happens in such a Hubble flow is that when photons are emitted from one point, let's say the photon is emitted here, it travels over here, it will arrive and it will have experienced a redshift here. Just as photons from galaxies, they arrive at the redshift, the same happens here. The photon, as it scatters from point to point, it's continuously redshifting with respect to the local frame. So what that means is that if you have lines here, maybe one line at 5100 and another line at 5150, these lines can cooperate to block the radiation. So this is called line opacity. And as I said, you have so many lines and you have such high expansion velocities that this can be important for many years. So most of the computation time in the simulations is invested into simulating this line transfer, which we do with the Monte Carlo method and with Sobolev approximation. The Sobolev approximation means that each of these interactions we treat as a purely local process. So that basically the velocity gradient of the supernova is so high that once you come into resonance with the line, you are in resonance over a very short spatial scale. So you can just treat that as a point interaction. So this simplifies the transfer quite a lot, and it makes the problem suitable for a Monte Carlo treatment. The code also includes a sort of, it allows you to choose how tightly you want to couple the radiation field to the level population solutions. In general, if you have a strong coupling and you have high optical depths, it can be difficult to achieve convergence. And then one can choose to sort of relax the degree of coupling. The way we do this is to split the model atoms into two parts. So we have sort of for the low-lying levels, we have a full coupling with the radiation field. Whereas for the high-lying levels, we can choose not to solve the level populations, but just treat them as a sort of scattering, as a bouncing target. And then we simplify the transfer. We do it in an approximate way. So this is something where you can use and allows you to sort of balance convergence with accuracy depending on which problem you are studying. Okay, so that was the methodology. We will look now at 3 different applications. The first application is determining oxygen production in supernovae. So oxygen is our 3rd most common element after hydrogen and helium, and it turns out that it is the element that is most sensitive to the progenitor mass of the star. So you see that in this figure here, you have the main sequence mass of the star on the x-axis, and you have the predicted amount of oxygen to be ejected by the eventual supernova on the y-axis. And the different entries here are different stellar evolution models. Now, if you plot this for other elements, there is typically sort of a growing function here. For hydrostatic elements, you tend to get more the more massive star you have. But not all elements are monotonic, and oxygen is the element that has the steepest dependency. So this is the first takeaway point. And it suggests something that if you're interested in determining the progenitor mass, if you want to say that was a 30 solar mass star or that was a 10 solar mass star, you should be able to use the oxygen production as the way to do that. You just have to say, do I see 5 solar masses of oxygen, or do I see 0.2 solar masses of oxygen from these nebular supernova spectra? Now, you do have variation here, of course. Depending on uncertain stellar evolution physics, you move up and down in predictions by maybe a factor of 2 for oxygen. But that is going to translate into some sort of error bar here, which one can live with, because this overall dependency is so steep that even if you have that uncertainty, you can make a meaningful prediction of this. The other way you can think about trying to do something here is to say, okay, let's say I know the progenitor mass by some other method. Maybe I have a progenitor image. Maybe I have a firm result by some other method. If it was 25 solar masses and I can determine the oxygen yield, then I can pick out which one of these stellar evolution model is the better one for this kind of star. But where we are right now, we are sort of focusing, for oxygen at least, we are focusing mostly on the first application. And this shows you a typical situation, or this shows you the degree of reproduction of observed spectra that we can do today. So the blue curve here is an output from SUMO, where we take a state-of-the-art stellar evolution supernova explosion simulation. We run it through this machinery, and then we compare it to an observed spectrum, which is the one in red here. And this is the sort of best fitting progenitor mass that we found for the supernova. This is a 15 solar mass star that has an oxygen mass of approximately 1 solar masses. And as we saw before, we have a very strong dependency on progenitor mass. If you now plot 12 solar masses or 25 solar masses, you see that the 12 solar mass gives you 2 weak oxygen lines. And the 25 solar mass star gives you 2 strong oxygen lines. And you also see the same signal in things like magnesium and sodium and so on. So one of the sort of first applications we can do is that we can say, okay, let us collect sort of observed oxygen line luminosities, plot them as function of time, and then compare them to prediction from the model grid. And what comes out of this kind of analysis is that the explosions of red supergiants, they are always ending up down here between 10 and 17 or 18 solar masses. And we are not detecting the kind of oxygen production that we expect from more massive stars. So we do observe red supergiants all the way up to about 30 solar masses. So we would expect to see hydrogen-rich supernovae filling this region of the diagram as well. But we are not doing that, at least so far. So there seems to be that these more massive red supergiants, they are in fact not exploding as hydrogen-rich supernovae. So then you start to think about what happens to these stars then. Are they not exploding at all, maybe? Are they just directly collapsing to black holes? Are they maybe becoming stripped envelope supernovae. So maybe they have a lot of mass loss at the very end of their life. It turns out when we do the same thing for stripped envelope supernovae, the picture is much the same. The best fitting models are always those with relatively low mass stars, say between 10 and 18 solar masses. And it seems then that the progenitor mass must have been something similar as to the type 2P supernovae. The conclusion from this is that these stripped envelope supernovae, the type 2Bs, the 1Bs, the 1Cs, they appear to come from relatively low mass stars that were stripped by binary interaction. So I just bring you back to this diagram here. So if you see the explosion of a star that had lost the outer envelopes and its helium core or nucleosynthesis corresponds to a 10 solar mass star, you cannot be in this regime. Because you only expect removal of the envelope once you go up to 30 solar masses. So it means you must be in this regime. It must have been a lower mass star where a binary companion was responsible for this. And overall, in the last decade or so, there has been a growing consensus, in fact, that most of the stripped envelope supernovae, they are coming from relatively low mass stars that have lost their envelopes by binary interaction. So from observed binaries, which seems to suggest that a really high fraction of massive stars should experience mass loss to a companion, to getting the best fits to supernova rates, mass inference from modeling supernova light curves, as well as in some cases, direct detection of a companion star. All these lines of research seem to point in the same direction, that these kind of supernovae come, in fact, from binary systems. So a relevant question to ask becomes, we would like, as astronomers, to know where oxygen comes from. And the current picture is not very satisfactory. The current prediction is the blue curve here. This is sort of, if you take a standard stellar evolution grid and you convolve it with the saltpeter IMF, and this is what is used in virtually all galactic chemical evolution models, for example. The relative production of oxygen should follow this curve here. So the most important contribution are from, say, 20 to 30 solar mass stars. Maybe 2/3 of the production should come from stars over 20 solar masses. We don't see any of these productions from supernova nebular spectra. So everything we see is coming down from this range here. So we have a bit of a problem in the sense that we are missing about 2/3 of the standard oxygen producers. So we don't know why this is. Is there something wrong here in the oxygen mass estimates, or is it simply so that the standard GCE models are not correct? And maybe a lot of these stars here are in fact not exploding as all as supernovae, but instead form black holes directly. I wanted to show you something about magnesium also. I see I'm a little bit behind my schedule here, so I think I will pass this one for now. Just maybe say that we are doing more things than estimating progenitor masses. We are trying to determine the relative production of things like magnesium and oxygen from the spectra as well. And there are some results on some quite recent results on this. I may get back to the details here later on the questions as well. And I think I will move on to the second application. So we have looked at hydrostatic nucleosynthesis, and we are now moving deeper into the supernova. We are moving into this innermost explosive region where iron group elements, as well as silicon and calcium, they are made in the supernova explosion. So here we are probing something quite different. You know, we are probing really in the way that the neutron star is formed and the supernova explodes. Nickel is, our stable isotopes of nickel are 58 nickel and 60 nickel. So these are neutron-rich isotopes. They have more neutrons than protons. And there is a very strong diagnostic line as 73-78 angstrom from nickel-2 in supernovae. Now it turns out that if one looks into the formation of this line and compares, for example, with the formation of this iron line over here, another way that you can use your forward models rather than just directly comparing to observed spectra is that you can look into the machinery of the line formation. So you run your complicated thing with all these, and then you see how are these lines formed actually. And sometimes what falls out of that analysis is that the lines are forming in a very simple way. So all the machinery with all its ingredients, it may say, actually, you don't need all these 99% of these processes. This is an optically thin line. It forms in LTE. Everything's very simple. It's not even very temperature dependent. And this is really good when we see something like this, because that means that we are able to sort of devise a method to determine the abundance where we know that the method should be robust or relatively robust. And this turns out to be such an example. These two lines here, nickel-2, 73-78, iron-2, 71-55, looking into the machinery of how they are formed, it turns out that they are a really good diagnostic of the nickel to iron ratio. And this means that we can just measure those two luminosities. We can apply a relatively simple analytic framework, and we can estimate the production of nickel to iron. This table shows you some results. So this is relative to the solar value. And what's interesting here is that core collapse supernovae, they seem to fall in two categories. Okay, there's one oddball here, which we ignore for now. There seem to be two main categories where you make either approximately the solar value, or you make something that is about 3 times the solar value. And then you can ask yourself, what is this telling us actually about the supernova explosion? And what I show you here is a prediction of the nickel to iron ratio, again in terms of solar. So you see the color coding here is, if you're within a factor 2 of solar, you're in the purple region. And if you're over, you're at this blue, and so on. And here you have the parameters of peak temperature and peak density of the shock wave that travels out in the supernova explosion. Now, if you look into 3D explosion simulations, you are typically in this regime over here. So that means that one can use these sort of simplified one-zone models to say what neutron excess of the fuel, which is the main parameter of the problem, do I need to get a certain ratio of iron to nickel. So the nickel has a positive neutron excess, the iron has 0 neutron excess. So the larger this neutron excess value is, the larger you are going to make this ratio. So it turns out that for 0.002, you make roughly the solar value. And if you change it to 0.006, you make a value that is 2 to 5 times solar, which is the values that we seem to infer from the second group of supernovae. And then very interestingly, you look into a progenitor model of the supernova, and what is plotted here on the y-axis is the electron fraction, which is 1 minus the neutron excess divided by 2, so sort of the inverse of the neutron excess. And it turns out that the oxygen layer of the progenitor, it has exactly a neutron excess of 0.002 in a standard solar metallicity model. The silicon shell, lying a little bit deeper, has a higher neutron excess, and the value is very close to 0.006. And then the iron core here, that is going to form the neutron star of the black hole, so that is not going to be ejected. So what you do is that you burn and you inject these layers, but it's not entirely known whether it's the silicon layer or whether it's the oxygen layer that forms this explosive nucleosynthesis ashes. The interpretation here seems to be that most supernovae, they indicate a neutron excess of 0.002, And that means that it's this oxygen layer that you are burning. And that would mean that the silicon layer actually falls into the neutron star or the black hole. But in a few cases, we see evidence of a much higher nickel to iron ratio. And to reach that, you must have burnt and ejected the silicon layer instead. So the picture looks quite appealing. There looks to be an interpretation there for these two groups. And if this interpretation is correct, it allows us to give a constraint on the way the supernova explodes and what happens in these very innermost layers of the star. So I come to the third application I would like to share with you of the things we do with this kind of work. This is results from last year. And it revolves around a very particular supernova called SN 2006 GY. You can see the light curve of this supernova here as the red points. And all these other things here, they are sort of normal supernovae. This is our most famous supernova, 1987A. It was down here, and here are some sort of representative light curves of other supernova classes. So this was a real oddball here. It was much brighter and lasted for much longer than any supernova that we had ever seen at this point. So in 2006, it was the brightest and was the most energetic supernova ever seen. And still today, it is up there in the sort of top 5 or something. So if you integrate the light under here, you find the radiated energy of order 10 to 51 ergs. And this is then approximately 100 times more than what we get out of normal supernova. Now, this was of the type 2N. So this is the type that you remember from the first plot, when we have sort of unusually large amount of circumstellar material that could come from a wind, or it could come from some sort of binary mass transfer process. There seems to be a really large mass of CSM present here. And the mass you can infer from this light curve and produce the spectral features is of order 10 solar masses. And not only that, you can infer from the velocity of the CSM and the radius of the CSM that these 10 solar masses were thrown out only 100 years before the supernova exploded. Of course, 100 years is extremely short in terms of any timescales we expect in stellar evolution, even for massive stars. So this is peculiar. Over the years, we have seen a really wide array of more or less exotic things involving pair instability supernovae, Eta Carina-like things that would explode after a giant eruption, like the one we had in 1840 and so on. Almost all of these scenarios, they involve some really massive star that is doing something that we don't quite understand yet. The last spectrum of this supernova was taken at 394 days. And it was very strange because it contained emission lines that we had never seen before in any supernova. And that's these lines over here marked by the blue arrows. This is very rare. Almost never these days do we see strong lines that we don't know what they are. We sometimes don't know how to make the line luminosities, but that we don't know what element we are looking at is almost never happens these days. So this was very peculiar. There were some lines identified from iron and calcium, that's the green and orange things here. But it remained a mystery what this thing was here. And clearly it held the key to understanding this supernova. But there was no solution to identifying these elements for over a decade. So we hope that the solution has finally come with what we propose in our paper from last year. And this solution came about, as always is in science, by not at all any kind of planned or coherent research, by coincidence. As we were computing spectral models for a completely different type of supernova, we saw that around 8,000 angstrom, under certain physical conditions, strong lines of neutral iron can emerge. And then we were sort of playing around with this, and this shows a zoom in of these 4 strong lines that were not identified before. And we can show that if you take neutral iron and you put it at the temperature of a few thousand degrees, and you have quite a lot of iron, you reproduce these lines quite nicely. And we normally don't see neutral iron in supernovae because iron is in the iron 2 or iron 3 state. It is almost always more ionized. So for some reason, this supernova, the iron is neutral. And the main suspect you have is that the density is high, because the higher density you have, the more neutral gas state you have. So this paper is a lot about trying to constrain the iron mass in the supernova. And the result we arrive at comes out to a very high number. So the iron mass is between 0.3 and 2.1 solar masses. Now, massive stars, they make core collapse supernovae, but they cannot really make iron larger than about 0.1 or maximum 0.2 solar masses. So this is problematic to match here. It's problematic to interpret the supernova as a core collapse process for other reasons as well. But just the iron mass itself seems problematic. Pulsational pair instability supernovae has been one of the leading candidates. Make no iron, and the model cannot work. And what about the 1A supernovae? They make half a solar mass of iron. It fits here. And could it be? So as we said, all analysis we have so far say that this is some kind of massive star. The idea we propose in this paper is that what if you have a white dwarf in close orbit with a giant companion? So this could be a red supergiant, it could maybe be an AGB star. And if you trigger an in-spiral process here, and you have a common envelope phase, could it be that the common envelope is ejected, and when the white dwarf reaches the center, the core of the other star, you have an explosion because you have a strong accretion onto this degenerate object? You would explain the synchronization, this 100 years between the CSM creation and the supernova explosion. You would get the right amount of iron, and you would solve a lot of problems with this. We test the scenario in the paper, and we get quite good results. So we take a 1A supernova, we decelerate it, and we do show that these neutral iron lines come out at least good flux levels. It's sort of a toy model, so we don't have exact reproduction of line profiles, but the scenario looks promising. And we also show that this very broad and bright light curve, that you can get that out in this scenario. So I'm running out of time. I skipped this. This is sort of some of the, if that's the correct model, how do you even get to that? We can maybe do that to questions also. I just wrap up in the last minute. Where are we now with this thing? So you've seen 3 different applications, 3 quite different sort of ways to work with the spectral models, 3 different ways to arrive at conclusions. We are working quite a lot now to get full 3D spectral synthesis modeling into place. So we have a 3D version of the code ready. It's not able to do the full problem yet. So it's doing like very simplified microphysics. And so far we have only used it to simulate some very simple processes. This is for example, predicted gamma ray decay lines and the line profiles you get out of 3D. And the reason you can do this is that the microphysics is trivial in that case. So we are fine with this sort of very simple code version. We have some toy models for iron lines, but we are still far away from doing realistic optical spectral simulations, but we are working towards getting there. And I think I will leave you with this figure. It gives you an overview of when it comes to nucleosynthesis diagnostics, where are we today in analyzing the yields in supernova ejecta. In green here, you see elements where we have a good diagnostic potential. We have clear lines. We have established methods. The blue is where we could get results, but we are not quite there yet. And the white are elements where we are either lacking good lines or the abundance is too small to do something. So I thank you for your time.
Thank you, Anders. So it was a very nice talk, very fascinating topic. I suspect there might be questions. So if you have a question, please mention it in the chat, and I will call out your name where I give priority to the more younger members of the audience.
I had a real summary slide put there also.
Okay. Okay, let's start with Tomer.
Yes, hi, thank you very much. It was really interesting. I have a quite technical question about the modeling, the code SUMO specifically. One of the assumptions you mentioned you are using is Sobolev approximation. I know that in the field of stellar winds, where it's a similar problems, where you have this expansion, this assumption has been relaxed because it was realized that it's not really valid. And I wonder whether in supernovae, if it's an issue, if it's something that one would eventually aspire to do, or is it a valid assumption?
Yeah, this is an excellent question, and indeed it's sort of, I think what one can say is that in all these sort of various physical processes that we simulate, you know, one always arrives at some level of approximation. My guess is that the Sobolev approximation is not close to being sort of our limiting our accuracy for the moment. There are things that we are doing that I'm more concerned about. For example, in this module of how the Compton electrons deposit their energies, there are things that can be done more realistically. We have some approximations in there. So that is one part of my answer. That yes, it's something we want to look at some point, but it's probably not our most urgent thing. Like one reason I don't think it's so urgent is that the velocity gradients are really quite extreme in supernovae. They're larger than in stellar winds, which means that you are moving sort of deeper into this the limit where you can assume, well, you need to assume that your physical conditions are constant over the Sobolev length. I think that is fine, unless maybe it's an unusually low velocity supernova, but for sort of normal velocity gradients, I think it's okay. Another part of my answer is maybe that there are certain things we do take into consideration. For Lyman alpha and Lyman beta, we have extreme optical depths often. So we know that the Sobolev approximation is bad. For those selected lines, we are actually implementing a more detailed treatment. So that thing is there in the code, like if some of the sort of stronger lines where the breakdown is most severe, we are doing more detailed simulation. And maybe that could be expanded in principle, but currently it's a little bit of manual algorithm there. Maybe the last thing I will say is we are moving into kilonova modeling. Here you have larger velocity gradients, which is good, but you have also many more lines, which is bad. So there it could be that this doesn't work anymore because you may start to have line overlap too severely. So it's something to look at down the line.
Okay, thank you very much.
Okay, then we have Pablo.
Yep. Hi, Anders. Thank you for the nice talk. I had a question regarding the large iron reservoir that you mentioned. Isn't this something you'd expect as well from very instability supernova? So essentially you can produce from nothing to tens of solar masses of nickel.
Yes, this is also a very good question. So I will bring you into my some reserved slides I have here. If I can find the right one. Yes, so your point is actually exactly correct. Pair instability supernovae can produce iron masses up to tens of solar masses. The theory prediction is, so pair instability start when you have helium cores at about 70 solar masses or so. So these are sort of extremely massive stars, and you get them up to about 130, 140 solar masses. And they predict the iron production predicted in this range varies from 0 basically at 70 up to maybe 30 solar masses at 130. So in this case, we need approximately half a solar mass of iron. And you can get that if you have a pair instability supernova from about an 80 solar mass helium core. So we did explore this model quite a bit, and you can get a nebular model spectrum out that is okay. You can get these iron 1 lines out, even if some other lines are less good. What made us unfavor this scenario in the end was that we could not reproduce the diffusion phase light curve with the pair instability. So to make this light curve, you need to have interaction, and no matter sort of what kind of CSM we put there, the interaction light curves never quite looked like the observed one. Whereas when we took a 1A supernova, the light curves came out much better. So this was sort of the main thing that we do not favor this interpretation. Then there are some other sort of more circumstantial arguments. The supernova was in a high metallicity region, which is very difficult to understand how to get the pair instability at high metallicity, because you expect a lot of wind mass loss to bring the star down to below the critical mass threshold. But so that is my answer. I would say it's probably the most interesting hypothesis besides the 1A CSM one, but we could not make all the observables work out eventually.
Okay. And how exactly do you set up the model to model the light curve from the type 1A scenario? So what sort of CSM do you build up for that?
Yeah, so we explored 2 types of CSM. So one was a constant mass loss wind, so it was an R-2 density. And then it was just 2 parameters. It was the mass of the CSM and it was the outer radius of the CSM. Let's see if I find the... And so we have this figure in the paper. This is the light curve, and here are sort of simulated light curves in the 1A CSM scenario. So we have 2 parameters, the mass of the CSM and the radius of the CSM. We also tried a constant density CSM, so just a shell, but we didn't get any sort of qualitatively different results from that. So we sort of stuck with this one in the main plots in the paper. Now, what one needs to do here, you need to have interaction going on here, and then you need the interaction to stop when you get to this last observation. This data point at 394 days after explosion, you have dropped by a factor 100 in luminosity. So this basically forces you to put an edge to the CSM. If you don't put an edge to the CSM, this interaction just goes on, and you're going to overshoot this. And the best value we typically got for the extent of the CSM was about 8 times 10 to the 15 centimeters, or a few times 10 to 15 centimeters. And then for that radius, one can vary the mass of the CSM. And then we found that if you have too much, you tend to sort of overshoot here, the light curve. and you tend to get too much deceleration of the 1A ejecta, the iron. Whereas if you have too little CSM, you have some problems here in the light curve, but mainly you don't have enough mass there to decelerate the iron down to the observed velocities at 400 days. An important point here is that, you know, if you take a 1A supernova as it is, the iron is expanding with 6,000–7,000 kilometers per second, whereas the velocity we see there in the final spectrum is just 1,500. So that you need to get the iron down in velocity by a factor of several.
Yeah. Okay. I'm still curious a bit what makes the difference if you were to put the same CSM on top of pair instability progenitor. Why would the light curve be so different if the energetics are similar?
Yeah, I think it's just your inner, your supernova ejecta in this case is about 1 solar mass.
Yeah.
And the other one is 100 solar masses. So there is quite a big difference in the sort of physical setup. But yeah, beyond that, yeah, I would have to dig deeper into giving you a more detailed answer of that.
Okay, thank you.
Okay, we have June.
Yeah, hi. Thanks, Anders. A very nice and very interesting talk. So I had one direct question and then one or perhaps two comments, follow-ups, so to speak. So regarding the modeling again, you mentioned toward the end going through 3D radiated transfer modeling, right? And my question there is that, of course, when one goes to 3D radiated transfer, you also need an input, so to say, hydrodynamic structure, you know, density and velocity. And in 1D, you mentioned you use a Hubble flow, basically, right? But in 3D, what type of models can one use there? Are you talking about then using full hydrodynamic models, or trying to use some sort of statistical approach to, say, the 3D density structure and the velocity structure in that case?
Mm-hmm. We do have now, so there are full 3D hydro simulations available now. So for a long time, the problem was that sort of the groups that were simulating supernova explosions in 3D, they were only doing, say, the first seconds or minutes of this process because of the computational expense, and they're mainly interested in, can they get the supernova to explode even, can they get the propagation of the shock wave out, and can they get positive velocities? Because historically, it's been a big problem in supernova explosion simulations that the stars tend to not explode in the computer. You have a beginning of a shock wave going out, and then it just doesn't have enough energy, so the whole star goes into a black hole, right? So there's been several research groups that have been doing sort of 3D explosion simulations for many years, but they would always tend to stop once they had the answer to this question, do I get the supernova explosion, and in case, what is my explosion energy, and so on. Now, about 5 or 6 years ago, the Garching group finally started to continue the hydrodynamic evolution up until you come to a coasting phase or a homologous phase. So we do have such models now. There's not so many of them. Maybe we have a dozen models or so, but they do evolve the supernova from the explosion phase up to several weeks after explosion. And when you come to several weeks, your hydrodynamic forces are unimportant, and you have sort of reached your final velocities for everything.
Yeah, and do you, so to say, on average, do they seem to reproduce some sort of 1D homologous flow, or are there very big differences? I mean, I know this is very difficult, of course, one doesn't know, but
well, I would say also when you have a 3D model, if you just wait long enough, you are close to homology, right?
Yeah.
Because it's just a matter of sort of at some point your parcel of gas has sort of reached its terminal velocity. And even if you have a non-radial component there, if you just let it expand further, you're going to align up more and more with the radial direction. And since we are doing this modeling at really late times, I mean, this is at least 100 or 200 days after explosion, we are fine as long as we have a model that is telling us the sort of terminal velocity vector of the things. Then we can sort of, I mean, even at say 20 days or 40 days, that is almost radial typically because the velocities are so high. And even if it's not, we can in principle extrapolate that and predict the homologous structure. So I think it's okay for this application. They are quite close to homology, these the models that we get out from the hydro simulations. Yeah.
Okay.
And the main difference is basically where do you have the elements, you know, which direction is the iron going, where is the oxygen, and it's just distributed in an asymmetric way, but still with a homologous flow.
Yeah. And then I had a final comment or some clarification that regarded your oxygen application and the lack of red supergiants actually. I think you had that there, since I don't see Dylan in the in the chat here now, so I will comment.
This one here, yeah.
Yes, exactly, because actually just also, so if I understood this, the oxygen abundance is here point, so to say, to a lack of observations of red supergiant progenitors above a certain mass, say 17, 18, right?
Yeah, so one can say that it's sort of two different methods that seems to point in the same direction, right? So they don't see these progenitors in the archival images, and we also don't see the expected oxygen yields from such stars. So
Okay.
I would say that's it's sort of two different ways to try to determine the progenitor mass of the star that exploded, and they seem to be in reasonable agreement with each other.
Yeah. Okay, that's very interesting because very recently, actually, we have from our group in Leuven published a new mass loss rate recipe for red supergiants, which predict exactly this effect when we implemented it, for example, in the stellar evolution code. That is that stars above, say, 17, 18, they seem to turn away from the red supergiant and go blue again before they explode. So that's something that we could follow up perhaps on discussing a little bit more.
Yeah. It's the problem though with this seems like a possible way to explain the lack of these objects for type 2 supernovae.
Yeah.
The problem though is, I mean, what happens if these stars eventually explode? I mean, they have to explode either as blue supergiants, and then they would become 87A-like things. So we don't see those kind of supernovae. Explosion of blue supergiants relative to red supergiants is something like 3%. So it seems like a too low number to sort of be hiding objects in there. And they don't seem to be exploding as stripped envelope supernovae either, because when we do the same exercise for stripped envelope supernovae, we always end up down here. So we're not finding them. And the only place I can think of hiding them is basically in the type 2N supernovae, so the ones that have strong interaction. It could be, of course, that if you have an unusually strong mass loss, you also more easily create an interacting supernova, type 2N supernova. And those supernovae, we tend not to be able to see the parts of the supernova because everything becomes masked by the circumstellar interaction. So we just see this interaction region, and we never sort of are able to find out what was inside of there. So that is one possible solution. And the other possible solution, I would say, are these 2L supernovae here. They seem to have less hydrogen. They are still red supergiants though, but they seem to have less hydrogen than type 2Ps, and they are not really well diagnosed for the moment. So yes, maybe there are a few places to hide them, but it's not so easy to do it.
Yeah. Okay, thank you. Very interesting.
Okay. I see that there are no questions, unless Dylan, do you have a question, or do you plan to discuss it during the upcoming
No,
coffee
I was
break?
just, no, that's fine. I was just responding to Jan's comment that I hadn't asked a question.
Okay, so then I would suggest to have a small break.
The work, just to clarify for everybody, the work I was referring to when I started, I was actually led by Dylan, which is why I made that comment.
Okay.
Apologize for that.
No problem. So I would suggest to hold a small break now, and then I give the floor back to Levin, who then will go on in a post-seminar discussion.
Exactly. So the discussion will be actually in the same channel. So if you're interested, you can just stay here, and we see you after a short coffee break.